All right, this video is going to focus on comparing tables. And we are going to compare the three types of functions, linear, quadratic, and exponential, that we know. And we are going to look at tables of each one and see what each one kind of does, what each one looks like, and maybe some defining characteristics of each one. The first section here is determine whether the table can be represented by a linear function. In other words, is this linear or not? The key to defining linear is that linear always has a constant rate of change. And this rate of change will either be addition or subtraction. And it'll be adding or subtracting the same thing every single time x increases by 1. Okay. In these tables, we always have x increasing by 1. Okay. So what that means we're looking for is we are looking for the y values to either always go up by the same amount or go down by the same amount. Okay. In this first part, from 10 to 7, this goes down 3. So we're expecting that to happen again when x goes up by 1. Okay, so if x goes up by 1 right here, this goes down by 3. X goes up 1 again. Y goes down 3. X goes up by 1 again. Y goes down by 3. Last one, x goes up by 1. Y goes down by 3. So yes, this is linear and has a rate of change of -3 over 1, or just -3. Okay? But because it's the same, -3 over 1, -3 over 1, -3 over 1, every single time, then we know it's linear. Okay? Over here, x goes up 1, y goes down 1. X goes up 1, y goes down 1. X goes up 1, y goes up 1. X goes up 1, y goes up 3. X goes up 1, y goes up 5. So for a few of these points, we have -1 over 1, -1 over 1, but then we have +1 over 1, and then we have 3 over 1, and then we have 5 over 1. So this rate of change is not constant, so this is not linear. Okay? Here, all of our x's are going up by 1. That is going up 25, up 25, up 25, up 25, up 25. All of these are going up 25. All of these are going up 1. So that is a constant rate of change. And that rate of change is 25 over 1 every single time. Okay? So that's linear. Quadratic, if you remember, the big thing about a quadratic is that it's got an x squared somewhere in the equation. So with linear, we expected the same thing to happen every time we went up by 1, and we expected the same rate of change all throughout this table. Okay, that's not going to be the case with quadratic, and I'll show you what will be the case with quadratic. Okay, let's look at this first one. That goes up 5, up 5, up 5, up 5, up 5. So the difference is always 5. The difference here is minus 7.5, minus 2.5, plus 2.5, oops, plus 7.5, plus 12.5. Okay, now if we take these numbers and I'm just going to take them down here real quick, make that a little bigger. You see that they're not the same, okay? So it's not a constant rate of change, but what is the same is the difference between the differences, okay? So the first differences just going down the table weren't always the same, right? We had 7.5 and then 2.5 and then 2.5 and then 7.5 and then 12.5. So those weren't at all the same, but the differences between the differences are always the same, okay? This is plus 5, this is plus 5, this is plus 5, and this is plus 5. And since those are all the same, the differences of the differences, then this is quadratic, okay? So in order to be a quadratic table, then the differences of the differences have to be constant. Okay? Let's look at the next table. This is going up by 1 every time. So that's a plus 2. That's a plus 0. That's a minus 2. That's a minus 4. That's a minus 6. So obviously not linear because these are all different. If I look at the differences of the differences, this is 2, 2, 2, and 2. And it's minus 2. It's going down, the differences. So the differences of the differences are all the same. They're all negative 2. So this is quadratic. All right. The next one, the difference here is plus 19, plus 7, plus 1, plus 1, plus 7, and plus 19. And the x's are all going up by 1s. Then differences of the differences, that's minus 12, minus 6, 0, plus 6, plus 12. The differences of the differences are not constant, they're not the same. So this is not quadratic. Okay? Exponential, we just finished up this unit, so this should be pretty fresh in your brain. The one learning target that we had was all about writing a equation from the table. And the first thing that you always did was you tried to find the multiplier. So that's the first thing I'm going to do here. In order to find the multiplier, look at 300 divided by 200. and that's 1.5. So this times 1.5. Now let's see if we do 300 times 1.5. Do we get 1800? Well, that's 300 plus another 150. That's 450, which is not 1800. So we can find the multiplier between this, but it's times 6. To be exponential, it has to have a constant multiplier, whereas linear had a constant rate of change, but it was all addition or subtraction. This has to have a constant multiplier. And it doesn't. We just showed that it doesn't. So this is not exponential. On this next one, find the multiplier here. So we're going to do 180 divided by 120. And that gives us a multiplier of 1.5. Then 270 divided by 180 gives us a multiplier of 1.5. 405 divided by 270 is 1.5. 607.5 divided by 405 is 1.5. And 911 2500ths divided by 607.5 is 1.5. So it does have a constant multiplier. So it's exponential. We'll do the same for the last one, 2400 divided by 4000. This is decreasing, so we know the multiplier is going to be less than 1 because it's a decay. So this is multiplied by 0.6. This is multiplied by 0.6. Point 6. 0.6 again. And the last one's still 0.6. So this has a constant multiplier, and it's exponential. All right. We're going to treat this as kind of a before class. So I want you to do these three. Try them on your own. Look at each one, decide if it looks like it might be linear, quadratic, or exponential. And then if it, say, is linear, find what the constant rate of change is. If it's quadratic, show the differences of the differences to show that it's a quadratic. If it's exponential, show that it has a constant multiplier. Okay. Then we'll go over this in class and discuss any questions that you have.